So in the previous lecture we stopped at this stage. Today we'll start from this one. So in this equation, if you can see this term, the Q and Rn is nothing but let's assume that there are the charges are distributed like this in the following way, like there's Q1, Q2, QA, Q3. There's so many number of Qs, and then it is separated by distance R1, R2, R3 like that. So there are Q number of charges and are distributed by Rn. This summation is nothing but the dipole moment, which can be represented as nu. So this is nothing but the dipole moment of the molecule. So what you can do is, instead of this term, the QRN, you can write it as nu epsilon cap. Okay, so you just have to write that. So these three terms becomes nu, and finally you can write it as this. Okay, so in this equation, this part, this is nothing but the projection of the dipole moment on the electric field vector, which governs the selection rule. So you can write this as, oh yeah, but before that I can do something else. What I can do here is that E naught and epsilon cap is nothing but E. So I can write it as E naught epsilon cap is equal to E. So I can rewrite this equation to be like this. So this becomes like this. So here we can conclude that this one over here is the selection rule, and I'll write it down, is proportional to this one, and this is nothing but the transition moment integral, which determines whether the transition will happen from one place to another or not, and this is therefore called as a selection rule. Okay, let's take a simple example. Let us suppose there's an electromagnetic wave, and this is the direction of propagation of the wave. Okay. The vector electric field vector, when it goes down, it is minus. Okay, now let us consider a diatomic molecule A and B. So this is a single diatomic molecule. Let us consider A as positive and B of negative. The direction of nu will be this side. Okay, now let's take three cases where first one, electric field vector epsilon is perpendicular, epsilon electric field vector is parallel, and then at certain angle. Okay, let's take each case. If E is parallel or perpendicular, so it's like this, nu is this direction and epsilon is like this, then E dot nu is 0. So what this means is that under this condition, molecule will not absorb light and there is no transition. But if this is parallel to nu, then E dot nu is not equal to 0. Okay, this is also same for certain angle. This will not be equal to 0. So that means there will be some transition. The transition moment integral will be non-zero. Then the transition probability, what will that be? So I'll write it as no transition there will be transition. In these cases, the transition moment integral will not be 0, and therefore we can write the transition probability to be Pf of t. I have written this equation above somewhere here. Here. This formula. Pf of t is equal to 1 by h cross square modulus integral 0 to t prime e raised to minus I omega if t, then this one. Okay, we found the value of this. Now we just have to substitute that to this to here and rewrite the formula. So I'll just copy this equation and paste it over there. And for this one, we just found out the value. I'll also copy this from here and paste it over there. Okay, and then we just have to substitute it. So directly we can do it. Okay, so Pf of t is nothing but 1 by IH cross square in modulus, or you can take few terms outside the modulus. You can take these terms I and this term, you can take it outside and it becomes okay, it becomes like this. Okay, fine. So this becomes E naught square, this thing, and omega if divided by omega the whole square. I square modulus becomes this thing, so that is fine. And then the rest of the terms, write it as it is. You will get like this. So the point to be noted is that in the earlier substitution, I mentioned that this and this term can be written as E, but here I'm not taking that substitution. I'm taking the equation before that. I'm keeping E naught as it is and writing the formula. Okay, fine. So you'll get the amplitude of that. So till here it's fine, I hope so. And now what you're going to do is you just have to substitute cos omega t to be 1 by I omega t plus e raised to minus I omega t divided by 2. That substitution you have to do, and then again solve it. It's just a simple substitution. Okay, and this term minus omega if is nothing but plus omega fi. So I can write that this thing here, and this becomes, and then okay, so this term becomes omega fi, and then I have to open it, so it will become omega fi plus omega t I omega t, and okay, I'll take comment like that, fi minus omega t. Okay, from if it becomes fi, that's it. Okay, fine. So that's the next substitution. So here when we apply light to a molecule, which is, it is called perturbation. That means, so this is perturbation happening. This is t is equal to 0, and this point is t is equal to t dash. This is from minus infinity, this is plus infinity. So here you can see that there's no perturbation happening here, and here also there's no perturbation. The only perturbation which is happening is in the range from t is equal to 0 to t is equal to t prime. So if we change the limit from 0 to minus infinity and t prime to infinity, it will not make any change in the working principle. So we can just change the limit of this one to minus infinity to plus infinity. One can write a Fourier integral of two conjugate variable to be like this. So del x minus a is equal to 1 by 2 pi minus infinity to plus infinity dy e raised to I minus I x minus a y, where this one is nothing but the Kronecker delta function. If x is equal to a, then it is 1, and if x is not equal to a, it will be 0. Okay, and now if you compare this equation, this form in this equation, the only term which is missing here is the 2 pi term. There's a pi term missing. So what you can do is just multiply and divide it by pi. So rewriting that equation, pf of t is equal to, you just have to multiply and divide it by pi. And also distribute, you can distribute this half inside, so you can make it as a 2 separate integral. Okay, so I just substituted that, and I wrote it in the Fourier integral form, and then just multiplied and divided by pi. Okay, so this thing, what can I write it as? I can write it as this, del of x minus a. Here this is nothing but del of omega fi plus omega and omega fi, sorry, del omega fi minus omega. Okay, you just have to rewrite this thing to this, like this. Okay, fine, in this form. Okay, and now that so here del omega fi plus omega, if omega fi is equal to omega, it's just 1, and if it's not equal, then it is 0. Similarly for fi minus omega, if omega fi is equal to minus omega, then it's 1. If it is not, then it's 0. So what the conclusion here is that these two things cannot exist simultaneously. Okay, so what that means is that omega fi, which is equal to minus omega, is stimulated emission. This is stimulated emission, and positive omega is stimulated absorption. So that means absorption and emission cannot occur simultaneously. So one of these terms, one of the terms here should go. Okay, so I can write this as absorption. This is emission, this is absorption. Fine, so only one term exists, so we can write this equation to be h square divided by h cross square divided phi divided by omega's whole square, del, I'll take the absorption term, minus omega the whole square, and then the rest of the terms. Okay, so that's it. This is the probability of absorption. Fine, h cross is nothing but h by 2 pi, square of that is nothing but h square by 4 pi square. Okay, you just have to substitute that, and finally you will get it like this. So these pi square clubbed together, we can write it as pi raised to 4. So final equation will be like this: 4 pi raised to 4 e naught square divided by h cross square omega fi divided by omega the whole square, del omega fi minus omega the whole square, this term. Okay, so that's it for this video. See you next one.